Sorry, we don't want this, I don't think.
Was that your phone? Okay, yes. Yes, I'm going to be talking about joint work with Natalie Paquette and Arun Sharma, who's here. So we've been studying celestial holography, and one problem there is with celestial holography. Well, you know, much of what it is, as Andy was saying, the idea is you're supposed to be able to relate four-dimensional quantum gravity and asymptotically flat spaces with CFTs on the celestial sphere. Now, to get a really good understanding of this, we would like to start in a place similar to the original understanding of ADS-CFT. So Mallasena derived ADS-CFT by starting with this beautiful string theory construction. And he had a completely explicit example where a large N gauge theory, equals 4 Young wells, was related to some explicit gravitational theory. So the problem with celestial holography is there isn't such a construction so far, and our goal is to provide one. So one way in which we feel the lack of such a construction is that the celestial CFT doesn't have an independent definition normally. It's just normally defined to be the thing that gives you the right answer. It's built from the bulk theory. And it would be nice to have an independent celestial CFT, an independent bulk theory, and then be able to calculate both sides and check that they're the same. So we're going to be able to do that. We'll find some completely explicit, large N, two-dimensional CFT. It's extremely simple, it's almost free. And we're going to relate this to a gravitational theory on a certain asymptotically flat manifold. So the manifold is something I expect people haven't seen before. It's something called Bern space. But maybe just to give you a clue of what's going on, Bern space is it's conformally equivalent to the blow up at the origin in C2 with a certain metric. Okay, so the story is going to start, let's see, with twisted holography, because as I wrote on the slide but didn't say, to do this, we're going to put together two things: twisted holography, which is some subsector of ordinary holography, and twistor theory. Things which sound suspiciously the same, but actually are quite different. So let me tell you a little bit about twisted holography. So this starts with some work of Leonardo and his collaborators, who realized that inside N equals 4 Yang mills is this really beautiful and tractable 2D chiral algebra. It also lives inside N equals 2 superconformal field theories. So this leads to the question, can you find a holographic dual with this subsector of N equals 4 Yang mills? So Leonardo with Vanetti gave a proposal for part of this, and Davide and I went a little further. We come to this conjecture that there's a holographic equivalence between the topological D model and SL2C, which is a complex manifold, and this chiral algebra subsector of N equals 4 Yang mills. So this is very much in the usual Mallasena holography style, because SL2C is some kind of avatar of ADS3 times S3. Strictly speaking, it's Euclidean ADS3 times S3. Now, I feel at this stage, this is pretty well established. In our paper with Davide, we were able to match correlators in the planar limit. My student, Ku Zhang, was able to do some things for certain non-planar correlators. Davide with Kaji Budzik, they were able to match some non-perturbative aspects, even giant gravitons. So there's a lot of computational evidence for this proposal.
Can I ask you a question about that?
Yeah, sure.
Is there a sense in which the chiral algebra subsector is living on the boundary of the space the B model is on, or is that not a good way?
Absolutely. It lives on the boundary of hyperbolic 3 space.
So somehow the dimension of both the bulk and the boundary got reduced by going to this.
Yeah, exactly. So you want to think of this as we're localizing to some sub region ADS5 times S5. Okay. But as well as thinking of it this way, there's also a nice way to kind of think of it from first principles, kind of mimicking a lot of things original argument. So where we don't view it as a subsector of the physical strings. We just start with the topological B model. We place some D1 branes on a plane. Some strange coincidence tells us that the chiral algebra of the D1 branes is exactly the same thing that Leonardo and Travis are. And then we back react. That changes the geometry to SL2C. It gives us a kind of first principles argument for why this duality should hold. Okay. So this is one part of the story relating this B model with this chiral algebra. Oh, and I remembered that this is not so important. It turns out for kind of various reasons, we decided to study a variant of this. That'll be what will appear in this talk. And the variant is, again, the chiral algebra associated to an n equals 2 theory this time, but it's a famous family of n equals 2 SCFTs, including the theory studied by Seiberg and Witten in their famous paper. This is the matter content. And if we were to follow Leonardo's construction, you'd find the chiral algebra is the thing described here. It's some free theory with these OPEs, and then we do a BRST reduction. So it's an extremely simple thing. Yeah, anybody can go away and compute all the correlation functions just by doing little Wick contractions. And one important point is that in the bulk, there isn't really any coupling constant except for 1 over n. So in the boundary theory, there's no coupling, it's free. In the bulk, the only coupling constant is n. Okay, so this is only one part of the story. I want to use this together with twistor space to get something that lives on spacetime. So I need to remind you guys a little bit about what twistor space is, unless there are questions or anything. So twistor space, this is this beautiful story invented by Penrose many years ago. And it's a way of understanding solutions of physical PDEs in terms of complex geometry. So the starting space is, if you give me a 4-dimensional manifold, I'll give you a 6-dimensional manifold by taking the projectivization of the bundle of spares. It turns out that this only depends on the conformal structure, and it has a complex, this twistor space is a complex manifold, if and only if the Veil curvature tensor is self-dual. And various things you can put on your original manifold, like a metric, Ricci flat metric, this kind of thing, are reflected in fun holomorphic games you play in twistor space. And also, you can, if you put a holomorphic field theory in twistor space, you can just dimensionally reduce to M. So holomorphic field theories, like those coming from the topological string, will give you some kind of field theory on M. So now we can kind of see what we're aiming for. Can we find some manifold whose twistor space is SL2C, ADS3 times S3? Now, if we could find such a thing, then we would have a nice celestial top-down duality by composing the twistor transform, relating some field theory in twistor space to ordinary space with holography. This would relate some theory on M with a 2D chiral CFT. Okay, so this is the goal of what we're trying to build. Okay, are there any questions? Okay. We should ask though, what kind of manifold are we looking for? Because I haven't told you what structures this manifold should have. We do know that if I want to do the topological string, I'd better have a Calabi-Yau. So the topological B model requires a holomorphic volume form. But this tells us what kind of geometry we need in 4 dimensions, because there's a theorem of Lebrun, which tells us that having a Calabi-Yau form with some poles on twistor space is the same thing as having calorimetric with a vanishing scalar curvature. If you're a relativist, this is a little funny. It doesn't, Ricci curvature might not be 0. But this is the kind of thing we're going to find.
So can you say why is the volume form singular, have poles? What's the interpretation of that?
Right. So the volume. Let's see. Say this. It's kind of generally necessary for the volume form to have poles, just because twistor space doesn't have a volume form. But then you could ask, what does it mean to do the topological string when I include these poles? That's actually okay, because the size of the volume form is related to the coupling. So this is some kind of region where the string coupling is very small. It's like a technical part of the story.
Didn't a second ago you said you wanted to be on Calabi-Yau space?
Yeah, I want to be on a Calabi-Yau space with some kind of boundary. So the locus where there's poles, I'm thinking of this as boundary at infinity.
Yeah, so this is, I think this D1 and D2 are somehow supposed to be, are they related to the boundary of Minkowski space? That's what I was trying to understand.
No, there's the picture I have is, so this is my twistor CP1.
Yeah.
And this is a boundary over there, 0 at infinity. And then there's another boundary over here, which is the boundary of Minkowski space. So the presence of these divisors tends to break the Lorentz group to SU2 times U1. Yeah, so that's really how you see the structure of space-time. Okay, so the space we're going to use, it's a manifold just like this, with this scalar flat metric. And it's an extremely simple thing. As a scalar flat calorimetric, so particular as a complex structure. And as a complex manifold, it's just the blow up of C2. So it's a line bundle over CP1. And there's this ridiculously simple formula for the Kähler potential. The first term is the Kähler potential for flat space, and then you just add a log of it. Now it's true, but kind of surprising that this thing satisfies the scalar flat PDE, because the scalar flat PDE is not a simple thing. But if you go through the computation, for some reason it works. So this is some manifold that's asymptotically flat. It has the group of isometries SU2 times U1. So
does the coefficient of the log have to be 1 here?
No, well, I mean, in the beginning, when we do some back reaction, the coefficient of the log is n, but then you can just absorb it into rescaling the coordinates. Okay.
It's half Bob flat.
What was that?
It's the subtle part, anti-subtle part of the Bob flat.
Yeah, that's a consequence of being a scalar flat Kähler.
Sorry, I
Yeah.
know you had 4 manifold that scalar flat and Kähler is T4. Why does the volume form on T4 blow up?
The volume form of the twistor space of T4 blows up. Because if you say, let's just take flat space for 4, then the twistor space is an open subset of CP3. And the canonical bundle of CP3 is O minus 4. So we don't have a holomorphic section. Okay, now, if you go and look in some old papers of Claude Lebrun, you will quickly figure out that this has the right twistor space. The twistor space, if I look at the regular locus of the volume form, is SL2C. And we also, we could have realized that this was the right thing to do some kind of holographic story, because if you take some D1 brains wrapping a CP1 inside twistor space and you back react them, then you would indeed find Burn space. So there's an old paper of Sean Hartnell and collaborators which were suggesting way back 20 years ago that this is what we would expect.
This is better correct using what equation?
Right, so we're using, we're sourcing a Beltrami differential, which is changing the complex structure in twistor space. And then the equation is like d bar of the Beltrami differential is a delta function on CP1. So it's just a source. And you solve this equation in terms of the Bochner-Martinelli kernel, and we realize it gives you SL2C.
That equation somehow be derived is topological, from topological D1 variant.
Yes, exactly. Because the Beltrami differential is one of the fields of the topological string, and the way it couples to a brane is I just integrate it over the brane. So this is, if I just solve the equations in motion in the presence of that term, you'll get this.
Can I also think of this as coming from this holomorphic gravity in 6 dimensions? Or is that...
Yeah, because the space-time theory of the topological string is the holomorphic gravity.
Can you remind me? So the Beltrami differential is a 0.2 form, or what's it?
It's a 0,1 form on twistor space on X with volleys in the tangent bundle. But when it's Calabi-Yau, you can think of it as a 2,1. Okay, so now we have our proposed duality. Whatever the topological string on twistor space gives us something on Burn space, and that should be dual to whatever this chiral algebra is. So we need to figure out, what does this give us on Burn space? And there's going to be an open string sector and a closed string sector. So let's first look at the closed string sector. So the field of the closed string sector on twistor space is this Beltrami differential. And twistor people have all these games to figure out what that will give you in space-time. And it turns out to give you a scalar field, which is interpreted as the Kähler potential. And the Lagrangian is this rather cool functional called the Mabuchi functional, where I take some derivatives of the Kähler potential and I contract them against the Ricci curvature of the metric given by the Kähler potential. This is well known in differential geometry. People like to study the flow, geometric flows from this function, and so on. And it has the feature that the equations in motion are the scalar flat equations, which you can see by varying k in that expression. You might ask, why should I think of this as gravity? It's gravity the same way, Liouville theory or something like that. It's kind of gravitational. I'm not gauging space-time diffeomorphisms. I just have a scalar field giving me a metric, and it's coupled to everything else in the usual way, as a stress tensor. So it's like a gauge-fixed kind of gravity.
So why are you implicitly contracting the indices using the second derivative of k? Or
yes. I should have written Ricci curvature with upper indices.
So what are the dimensional parameters of the theory? You have some coupling constant in front of the Mabuchi function?
Yeah, it's either it's n or n squared or something like that. There's only one parameter.
Sorry, there's no graviton here?
Well, this is kind of like a graviton. It's certainly not Einstein gravity.
Yeah, but whether there's a propagating spin 2 degrees freedom?
There's a propagating spin 0 degrees of freedom, but its second derivative couples to the stress tensor of everything else.
So
So
there's no transverse spin 2. Yeah, there's no gravitational wave, say, as a transverse spin 2 excitation.
I don't know. I mean, it's possible to write. I mean, it's possible to write a gauge fixed form of ordinary Einstein gravity in terms of a single scalar as well. And then I'm not. But maybe Atul could probably answer your question better. So I don't.
But it's Euclidean theory.
It's Euclidean. You could write this in Lorentzian signature too. But when we get to computing amplitudes, everything just extends to Lorentzian signature as well. Oh, if we did it in Lorentzian signature, there would be annoying factors of I, and clearly not unitary. Okay, so what about the open string sector? This is this really nice thing that, well, appeared in Leonardo's talk, where it's a signal model on the group. And what we're going to take is, we're going to take this is the chiral Lagrangian that Leonardo wrote down. We're not going to use it to solve QCD. And this is this funny term. It's not the WZW term that Leonardo wrote down, it's a different one. Well, the meaning of this in QCD is you have a background U1 gauge field for the U1, for the baryon number U1. Because this current it couples to is the topological charge in the chiral signal model. Anyway, this model was studied by Donaldson and Nair. There's a lovely paper from Joseph Moore, Microsoft Chatishvili. And you find that the equations of motion are something called the Yang equation, studied by Yang a long time ago, because he had this matrix formulation of gauge theory. And it tells us that this current I can build for my field sigma satisfies the Yang-Mills equation. So we can think of this as a gauge-fixed version of Yang-Mills theory. And the amplitudes of this theory are all plus Yang-Mills amplitudes, at least at tree level. How am I doing for time, by the way? When do I stop? 20 minutes? Okay. Okay, good. I'm doing good. Yeah. Okay. Now, we want to build a duality relating, some kind of quantum gravitational theory and some chiral algebra. We might immediately object that the Lagrangians I wrote down were highly non-normalizable by power. Twistor theory really helps you here, though. It's really easy to write down all kinds of counterterms in space-time. Like we saw in Leonardo's talk, he wrote down all kinds of counterterms for the chiral Lagrangian. Basically, none of those can be lifted to Twistor space. It's extremely tight constraint. So I studied with Celie a long time ago, and we were able to show the counterterms can be fixed uniquely by the requirement that they come from Twistor space. And the theory is also anomaly free in Twistor space as long as we use SOH. So if you want to think of what this means conceptually, we have a string description of this theory in Twistor space. So even though it's non-normalizable, we have some kind of UV completion on Twistor space, which is why it makes sense at the quantum level. Okay, so far I've explained we have this Burns geometry, and we have this Mabuchi gravity. This Mabuchi gravity was some scalar field, which we interpret as a scalar potential. And I want to relate this to this large N chiral algebra, which is given by BRST reduction of a bunch of free fields. So the chiral algebra is extremely simple. And just to be totally precise, I mentioned that twistor space has this kind of extra boundary there, where it's a terrible picture, where the volume form is poles. That means we have to insert some defects in the CFT. So how does the dictionary work? So the dictionary works like it typically does in kind of chiral versions of celestial holography. If you're used to studying amplitudes on flat space, you know that to give a massless state, same as to give a pair of spinors, lambda and lambda tilde. Now, Bern space is close enough to flat space if this is still true. So what we're going to do is we're going to take lambda to be 1, z, and z will be a coordinate on the chiral algebra plane. So in this way, the momentum tells us where we are, chiral algebra plane, and the states will correspond to generators in the chiral algebra. And the basic thing we want to show is that collinear limits, if I have two states whose momentum becomes collinear, get a pole in any scattering process, I want to show that those poles are the OPEs of the chiral algebra. And I want to show that the amplitudes are correlation functions. Now, if I was really lazy, I would say, oh yeah, twistor space tells us this all must be true. End of story. But that's not really very satisfying. So what we're going to do is explicitly write down all the states, explicitly compute some correlation functions in OPEs, and match it with the combinatorics of the chiral. And when I say we, it was actually mostly Atom who did this. So we have to start by saying, well, what's a state? And I'm going to work in the open string sector, because that's easier. So the WZW4 model, it's a sigma model on SO8 to write down a state, pretty much the same as writing down a state in a free massless scalar. So I need to solve the Laplace equation in this geometry. And I want a solution that when I take the flat space and limit it by sending n to 0, becomes a plane wave. So, I don't know, somehow this turns out to be the solution. It's a kind of a complicated expression, but the thing to bear in mind is that it's a plane wave dressed by something. Now, I want to match this with this state in the CFT. So the CFT has fields that has 8 vectors there, I, and I have a pair of matrices, x alpha dot. Alpha dot takes, at index alpha dot takes values 1 and 2. So what we do is we say the CFT state is going to be just I times the exponential of x times I. And I will match that with the gravitational, with the bulk state. That's the proposed match between states. Okay, I think I'm going too fast. Are there any questions?
So you're looking at the open string sector, so these are flavor ordering.
Yes, exactly.
And how do you see this flavor ordering on the chiral algebra side?
Yeah, because let me draw a picture. If I have like an open string thing like this, I'm gonna, I mean, it's the same thing as in your talk, right? I'm gonna do a bunch of Wick contractions like that to compute the correlator. The flavor order you can see by this structure on the boundary. Okay, so the first thing we want to do is compute the bulk 2-point function. So this is just the 2-point function of our free scalar in this geometry. And we're going to compute it in the usual way one does compute holographic 2-point functions. We stick our state into the integral and compute that integral. Fortunately, this was computed by Hawking, Page, and Pope. It might be surprising why they cared about this. The reason is that the geometry we're using is conformally equivalent to CP1, CP2. They wanted to use CP2 as a gravitational instanton, and they had a conformally coupled scalar in their analysis. So because they're scalarly coupled, the conformal factor just doesn't matter. It's the same thing. Anyway, they found this nice formula in terms of a Bessel function. And it's important that the Bessel function has this expansion in terms of 1 over n factorial squared. So this leads us to the first check of the duality. If I want to compute the 2-point function in the chiral algebra, chiral algebra is free. It's just a bunch of Wick contractions, and I just get a bunch of powers of n and factorials, but they all match up perfectly. I get the n factorials because I have these exponentials here. So here, the number of x's, every x gives me if I have n x's, I get 1 over n factorial. There's powers of n from the n's I can stick in this thing, and then because it's a free, it's a free theory, I get a power of 1 over z12 for every line because I'm doing a good contraction. And if you sum these up, it is just the exact same thing. So I was pretty excited when Adol told me this. We didn't have to work so neatly, but it did. Okay. You might object, though, that you might just think, oh, what about the norm? Maybe this is just a clever normalization or something, and this is not really true. But so to get around that objection, I want to show you that we can match 3-point functions as well. We can match 3-point functions, we're really seeing something because we can't just fiddle around with the normalizations to get them both right. To do the 3-point functions, well, it's actually a little technically easier to do the OPE. And this is not so commonly discussed in the literature on holography, but I mean, people know about it. I just, do the diagram, the wooden diagram for a 3-point function, and I kind of just put a propagator on one leg. You can compute this very easily. You find it's a very elementary computation in flat space. It's quite hard on Berns space. But the first term is just 1 over z12, and then there's these corrections. So yeah, I feel bad. Adol was telling me you have to learn, go to the literature in quantum chemistry, find the right integrals, which will get him the second term in this expansion. What was it?
You have to compute Fourier transforms of multi-centered Coulomb potentials. Therefore, the analogs. Do not look it up.
Now, on the boundary side, it's completely trivial to do this. How do we compute the OPE? We just do a Wick contraction. And if you just eyeball it, you see it has the same structure. And to the order we can compute it, which is one more order than I've written down, all the coefficients match beautifully. And we can also, to a certain order, we can also compute the 3-point functions. Okay.
So making a distinction between OPs and 3-point functions.
Oh, yeah, there's no serious distinction in this case. I mean, if we were to work in flat space, the 2-point function would be 0, and then there's a distinction. But here, there's no distinction. Okay, so I'm going to explain most of what we know about the duality. There's a little more we're able to check. If you compute the conformal blocks of the CFT, the way I think about this kind of thing is that conformal blocks should be states of the 4D theory, which you can, is more or less the operators wrapping the CP1 in the middle. And we can check this.
How do you compute the conformal blocks?
But this, Well, you take the CFT in the planar limit, and basically each open string and each closed string looks like a free field. So that gives you kind of 1-point conformal blocks, and the whole thing is like products of the ones.
Okay, so it's important that you do this analogy because I find anything to be quite hard.
Absolutely, I find it, and you do not know how to do it. Yeah. Except for n equals 1, because one of your papers, you have this paper where it's SO8 at level -2.
Yeah, but that is also hard.
Is that also hard? Okay. Okay. So what the way the duality is going to work, as I said, is the OPEs are going to be the collinear limits in the bulk. The correlation functions, I can take the correlation functions in a conformal block, they'll be form factors in the bulk. So there's a lot to, I mean, we've checked some of this duality, but it tells you, if you believe it, it tells you kind of an astonishing amount about this 4D theory. So my last slide. So the summary is, by thinking about twisted holography plus the twistor transform, we derive this duality relating an unusual gravitational theory to a simple large NCFT. Now, the gravitational theory is UV complete, and we were able to do a bunch of computations on spacetime, on Bern space, to really check the duality. Now, what I find really exciting about this, let's assume that this duality works. We know this CFT at finite n. It's very simple. Does that tell us we know this gravitational theory of finite coupling? It seems to. I mean, but that seems, I don't know, far too strong. I don't know. There's all kinds of weird, at finite n, the states of the CFT really collapse. There's many fewer of them. What does that tell us about the gravitational theory? I have no idea. There's all kinds of mysterious things about that, but I think I will stop there for questions.
Sure. In the old twisted string story of Witten, we know that starting from a local theory in twisted space, you just get like self-Young mills, but then you add something like the sentence or ingredients, and you reproduce some Young mills and some Young extension. Is there a sense in which Mabuchi gravity is a kind of starting point toward Einstein gravity in a similar way?
I don't know. I think it's too. Like, for instance, the kinetic term is fourth order. So I feel it's a bit strange to try to change it to become Einstein gravity. And I also think that they're never going to get, it has local operators. Einstein gravity doesn't have local operators. It would be a pretty drastic change.
So the Mabuchi gravity is UV complete by itself. It's not that it's UV completed to the topological string.
I would see. Not quite sure how to answer that. I'm a bit of a kind of working class guy somehow with this stuff. And for me, UV complete means I know what all the counterterms are. And the reason I know what all the counterterms are is kind of because of the topological string. So I don't.
I mean, normally you would say, oh, there's a lot of, it's sufficiently high energy, or there's actually new modes that weren't there in this gravity theory. That's what we would say for string theory.
Yeah, no, okay, maybe in that sense it's a little different. Perhaps I hope not misusing the phrase UV complete, because in the physical string, it's not just particles. You could get the winding modes from strings of finite length, but you don't get that in the topological string. The topological string is always kind of shrunken to a point. So,
you're making it similarly about content terms or the periodic integration.
Exactly. Maybe that should not be called UV completion.
I see. So, this thing you said at the end that was surprising, that at finite n you would have finite number of states in the, well, I mean, why is that? Isn't that always what happens with holography?
I suppose it is, yeah. But I suppose I find it intriguing here because I feel we have really good better control.
Mhm.
In ordinary holography, you have to deal. You not only do you have n, you have the additive coupling, and makes life much more difficult.
Yeah. I mean, but we sort of understand in some limited sense how it works from a bulk point of view, because when you start computing overlaps, you find that your states you thought from an effective field theory point of view were orthogonal are not really orthogonal, and then you start counting and stuff. And yeah, so I mean, is it conceivable there's a similar calculation here on the bulk side?
Absolutely, yeah. I mean, I think I just didn't know what the usual explanation was, but yes, I think it absolutely is conceivable.
And then I have one other question. So is there a way to deform the boundary theory away from being free? Is there an interaction direction or anything you could turn on?
I don't think so.
Oh, really? It's just rigid, like it has to be free, it can't be.
But it's free in a very strange sense. Like you're considering gauge invariant operator and one-over-n expansion. So they have a very intricate one-over-n expansion.
So it's like generalized free field. I mean,
well, I don't know. Free is in the end of the beholder. It's a VLSC reduction of a free theory, but the theory itself has a very complicated OPEs.
Exactly, because you don't have access to the free fields by themselves.
Okay.
You only have access to these composite things.
Okay, but does it have a marginal deformation?
No, I don't think so.
No, it doesn't. But one thing you could do, of course, is to introduce the anti-chiral half in an attempt to construct a full-fledged 2D CFT.
Yes, absolutely.
Now, what would that be dual to in 4D? I have no idea. But
yeah, me neither.
So this is not so straightforward, of course, because these VOAs are some funny logarithmic non-unitary VOAs, and nobody has ever constructed a full-fledged CFT. But in principle, it should be possible. So that theory, of course, is going to be a lot more intricate.
Yeah, I mean, if I want to do that, I'd want to do some kind of sphere construction with your Q plus S bar, gluing them together from n equals 2.
From the 2D perspective, this is something you could entertain, right? You could ask, what is the full? Is there a full-fledged 2D CFT has this VOA? I think there's certain indication that's the case for n equal 1, like SO8 level -2, but nobody is fully constructed.
Yes.
So why did you do this particular case and not I didn't understand that part. Why didn't you try to do the similar things for the n equal to 4 chiral algebra?
Oh, it's just because when I put n equal when I put the bulk thing on twistor space and reduce, you just get something kind of weird. You get the Mabuchi gravity plus 2 fermionic scalars. It's like, I don't know. I just thought that was kind of ugly. That's all.
And could you try? So there are, on the other hand, perfectly good, honest to God, rational chiral algebras that emerge in our story. They're non-unitary, but they're rational. So those 2D CFTs we know. For example, you could get some non-unitary minimal models with arbitrary large negative central charge. Is there any sense in which we could repeat the game there?
I think you can repeat it for any family of n equals 2 theories which has a holographic jewel. So if that includes those examples, then it should.
Because there the 2D story is a lot under Bellatin. You will land literally on some exact solvable, fully non-chiral 2D CFT.
Were you gonna ask something, Andy?
Yeah, are there a finite number of primaries in this conformal?
At infinite n, no.
The finite n.
Finite n. I don't know. Leonardo would know.
So it's complicated. So this is a logarithmic VOA. So there's a finite number of simple ordinary modules, but uncountably many models which are irreducible, but non-decomposable. So it's a funny story. So it's not a rational. This is not a rational thing. So it does not have a finite number of modules altogether. But if you just want ordinary modules, the one where, for example, L0 is bounded from above and below, then there's a finite number of simple such modules. There are examples. For example, you could take SU2 level -4, which is the simplest example of theory in this class. In there are, it's a bit fun. It's the mathematics of this is still a bit of a work in progress because of these peculiarities. But there are proposals for how to construct a modular and bare partition function, ultimately just use a finite number of modules. But the theory is not rational in the conventional sense.
So does that mean that in space-time there's infinite number of particles?
I feel like the modules are more like, well, we can construct some modules by thinking about twistor space. And they tend to look like strings. I don't know if that's what all modules will look like.
So it's a kind of a Zeri-esque theory.
I think so. I think if we wanted to try to
There are infinitely many particles, like age invariant operators of specific length that in one-to-one correspondence with the infinitely many soft currents in bleeding, subleading, subsubleeding, and so on. And when you recombine them, it becomes a single hard particle. It's like
So there are multiplets of,
yeah,
there's some finite number of them.
it's like an integer basis. So it's labeled by discrete, the length of the operator.
So it's a little confusing because there isn't a translation. So we can't
There's no
think of
translation.
what they're multiplets.
Then multiples of the remaining isometries of backspace.
SU2?
SU2 cross U.
I see.
They take, right?
yeah.
Okay, well, if there are no more questions, let's thank Kevin again. Coffee break.